Swayam Prabha. Digital India. Educated India.
So what is to notice from this slide is capital delta A as well as U bar TA are constants that depend on the problem instance. Okay, they're constants. The other things, right, this little ZTA, capital ZTA, U, these are either events or random variables. Okay, they will, each time you run the algorithm, they might take a different value. Okay, and of course, you should not get confused. The fact that there is a well-defined capital delta A and U bar TA does not mean that the algorithm knows what these are. Okay, these are things that we are using in our analysis. The algorithm itself will do what it does. It looks at history and decides which arm to pull, right? So don't sort of mix these two things up in your head. The algorithm did what it did on the previous slide. Of course, the algorithm does not know things like capital delta A, but we will analyze the regret of the algorithm, and quantities such as capital delta A will show up when we do that. Okay, all right. So our proof is going to be in 4 steps, and we'll begin with step 1. Okay, so I mean, as we go along, I will tell you what is happening in each step. But the first step is fairly intuitive. So the first step is simply going to establish that if we want to upper bound the regret, really what we should be trying to upper bound is the number of suboptimal pulls. Okay, for each suboptimal arm, how many times are we pulling that? If we bound that number, then that can quickly translate into a bound on the regret itself, right? So more specifically, quantitatively, what we are going to show is that the regret can actually be written down as the sum over the suboptimal arms, the expected number of times that arm is pulled, multiplying capital delta A for that arm. Okay, I mean, you might just actually write this down. It just seems true to you, but we can actually prove this, okay, using what we had introduced as notation. So how do we do that, right? One step at a time. So first we start with the definition of RT, okay, which you are familiar with. And what are we doing as a first step? Well, there was an expectation here of RT, right? Why is there an expectation of RT? Because we don't know which arm is actually being pulled at time t, right? We do not know what AT was. That itself is a random variable. So because that is a random variable, we can write down this expectation as a sum over all the arms of the probability that that particular arm was played. If that arm was played, then we know that the reward is being generated according to the empirical, so the mean of that arm. Okay, so if ZTA has happened, right, we know that maybe arm 3 got pulled, then we know what the expectation of RT is going to be, right? It's going to be the actual mean of that arm. All right, so this is just one step in terms of expanding out this expectation by bringing in the arms, right, and the probabilities that those particular arms were played at time t. Okay, next step. Now I'm going to use what we did on the previous slide. We know that probability of ZTA is the same as expectation of little zTA. Okay, that's already shown. And we also know that if ZTA happened, right, then RT, the actual reward that you got is the mean of that arm, which is PA. All right. Okay. So this is a relatively straightforward step. What's happening next? What's happening next is I'm doing something to both the first term as well as the second term. Okay. So the first term was P times P star, right? But you'll agree with me that P can also be written as the sum of the UTAs for all the arms, right? If you add up how many times each arm got pulled, okay, whether an expectation or not, right? In fact, you don't even need the expectation here. That quantity is going to be T, right? So I'm just replacing T by the sum of the number of pulls of each arm. And over here, I'm keeping the sum over arms, but I'm going to say that if you sum up expectation of little zTA over time, right, through the horizon, that's going to be the expectation of UTA, okay, because the ZTAs add up to UTA. It's inside an expectation, so you keep the expectation. The PA stays PA. Now, having brought it to this form, we can sort of collapse these two things together. There's a sum over UTA that's happening in both of them, and then if you combine them, you get a P star minus PA, which we know to be capital delta A. All right, which is basically the proof that we were looking for. Okay, so I mean, this is just making it very crystal clear that we can actually formally prove something even as simple as this. The key is to define the quantities ZTA and capital ZTA. Okay, that's basically what we used in this proof. So, having sort of established this small result, right? Take a minute to convince yourself that it will suffice for now to show that each arm A, right, in expectation is pulled order of 1 over capital delta A squared log T times. So why is that? We have just shown that the actual regret is the sum over suboptimal arms of this multiplied by delta A, right? So if this multiplies delta A and you sum it up, the regret is going to be sum over 1 over delta A log T, right? And that was the bound that we were anyway looking for. So going forward, our focus is just going to be to show that the expected value of UTA for arm A is order of 1 over delta A squared log T. Okay. So up next is step 2. Okay. So again, what is this step? This step is going in the direction of bounding the number of poles of suboptimal arms. So what we are going to do in this step is to divide the poles of a suboptimal arm into two regimes. Okay. So we have to show that expected number of poles is order of 1 over delta squared log T, right? So how we are going to do that is to show that LHS is actually upper bounded by U bar TA, which we know is in that same order, plus a constant. Okay, and the way we are going to do that is actually to give the arm U bar TA samples for free, right? Say, well, we're not even going to try and bound. Let's assume it's given so many samples, but thereafter, I mean, the arm having been pulled so many times will have to behave itself, right? And in that regime, we will say that it cannot be pulled more than a constant number of times in expectation. So let me lay down the steps, okay, for doing this. We know that expectation of U capital TA is sum of the little z TAs, and by the equivalence we have shown before, that's the sum of probability of capital ZTA. Now, probability of ZTA can be written down as two things. Okay, so UTA, right, the number of times arm A has been pulled, that's either going to be less than U bar TA, which is a constant, or greater than or equal to that, right? So these two events are mutually exclusive ones, and I mean, it's got to be one or the other, right? One is the not of the other. And therefore, you can divide probability of ZTA into two separate sums of probabilities, okay? Which is what we have done over here. And our effort coming up is to show that the first of these sums is upper bounded by A, and the second is upper bounded by B, okay? And if we do that, right, then we will thereafter say that A itself is upper bounded by U bar TA, which is what you saw over here, and B is upper bounded by a constant. Okay, so because of the number of times the arm has been pulled, the way we analyze these two terms is going to be slightly different. Okay, the first one is actually relatively straightforward. So look at what's going on in the first sum. We are looking at the event that ZTA happened, which means at time t, arm A got pulled, and also the event that the number of times, the number of pulls was less than U bar TA, right? Now think about it. If you sum this up over time, right? I mean, each time ZTA happens, U is going up by 1, right? So the number of times both of these can happen, I mean, it has to be at most U bar TA, right? It cannot be more than that. So that's actually like a easy way of saying that U bar TA should be like an upper bound on A. But we will actually say it more carefully and rigorously, because I think it's worth the effort if you're doing it for the first time. The second term, right, is when the arm has already been sampled enough times. enough being u bar Ta. In that regime, to show that you won't have too many pulls is really where the elements of UCB, Heffding's inequality, things like this come into the analysis. Okay, and so we are bifurcating now into bounding A and bounding B, and let's say step 3 is that of bounding A. Okay, so let's go through the steps for saying this formally. So A was this sum that we had written down, sum over time, that probability of Z, capital Z, Ta happening, and UTA being less than U bar Ta. Now I'm just going to write this down, the sort of probability term, more explicitly. Okay, so what does it mean when you say that UTA is less than U bar Ta? So what you actually mean more in grounded terms is that UTA is either 0 or 1 or 2 or 3 or U bar Ta minus 1. That's what you mean when you say UTA is less than U bar Ta. So actually we have written down each of those as a disjunction. Now again, because these are exclusive terms, right? When A and B are exclusive, probability of A or B is the same as probability of A or plus probability of B, right? So you can include here as a sum of M, okay, that's the number of pulls going from 0 to U bar Ta minus 1 of probability of ZTA and this exact equality, okay? Now, the next step is just interchanging the sequence of these sums. Okay, here we summed over T and then over M. This thing here depends both on T and M, right? But I mean, you can also do it the other way around. So the only thing we're doing here is first summing over M and then summing over T. Okay, but now there is a sort of interesting angle to this, which is really where the heart of the proof lies. Okay, so this sum over T of all these probabilities, right? What is it? It is a sum over time that ZTA happened and UTA was exactly equal to M, right? Now, UTA being equal to M, right? If UTA was M and ZTA happened, now what does this mean? It means U for the next time step cannot be M, right? It's got to be M plus 1. All right, so we use the fact that if this event happens, right? If ZTA happens and UTA is M, then it cannot be that UTA remains M. Okay, I mean, for the next time step, UT plus 1A must have changed. So therefore, take a minute to convince yourself that this sum of these probabilities, right, can actually be written down as the probability of a single event that is a disjunction. Okay, so just to save space, I'm replacing and by just a comma. Okay, so the probability of these smaller events summed up, right, I'm claiming is the same as the probability that at time 0, Z happened and U0A was M, or at time 1, Z happened and UA was M. Right, so UA basically can be M only for one time step in which the arm gets pulled, right? So this or this or this, these are exclusive events, and therefore, I mean, it's maybe a little bit easier to go in the other direction, right? Suppose I had given you this first, right? Probability of this for 0, this for 1, this for T minus 1, right? You can see that only one of these things can happen, right? If because one of them happens, then M ought to have sort of gone up by 1. It cannot happen for anybody else. Okay, so there is exact equality between these two things. Okay, that's why we have an equal to over here. So this is sort of subtle step. Okay, but this is the important step in this calculation. But if we do it like this, right, it now becomes somewhat trivial to argue that we are summing up from M going from 0 through U bar T minus 1, these probabilities. Well, we know that probabilities are all upper bounded by 1. Okay, so just upper bound, put a less than or equal to here and replace this probability by 1. If you do that, then you get U bar Ta. Okay, which is what we had set out to do. So what is the fact that we have used here? we have used the fact that for I less than j, okay, I and j are between 0 and t minus 1, only one of these things can happen. Both of them can't happen. If zai and uai is equal to m, then we can conclude that not of this, right? It cannot be that zj a and ja equal to the same m. Okay, that's the fact that we have used to go from this to this. Okay, so in general, right, when you do a union bound like this, there will be a less than or equal to if they are not exclusive. We have very carefully used the fact that they are exclusive. If they were not exclusive, right, they would actually be a greater than or equal to over here, which is not okay in the direction we're going. We're able to get by because there is exact equality. So honestly, this is not like a great slide. Okay, this is not really the reason we are able to get a bound for UCB. This is relatively, I think you can also argue it intuitively, but if you want to argue it mathematically, here's the way to do it. Okay. Okay. So bounding A, we wanted to show that A is at most U bar P A, and we have done that on this slide. Step 4, right, is to bound B. Now that's going to be a little bit more challenging for us. It's not as easy as what we did. We'll actually have to bring in elements from UCB. We've not really touched UCB and the way it is sampling so far, right? So that's going to happen in step 4. And step 4 itself is going to be in 3 parts. Okay, so let's look at step 4.1 first. You're going to encounter a little bit of very subtle, big looking equations right now. Okay, but maybe have a cup of coffee or something and do it slowly and steadily. All right, so remember that B was the sum of these terms where ZTA happened, but UTA was larger than or greater than or equal to U bar TA. Okay, now let's see why this would happen, right? If ZTA happened, right, what does it mean? It means arm A got pulled, right? Why would an arm get pulled? Remember that we are running UCB, right? An arm gets pulled only if its UCB becomes the maximum UCB, right? So in particular, we can say that if ZTA happened, then the UCB of arm A must have exceeded, in particular, the UCB of the optimal arm, right? In fact, it should probably have also exceeded other UCBs, but we will restrict ourselves to saying if arm A got pulled, it had a higher UCB than or greater than or equal to, right, that of arm star. Okay, the other part we just leave as it is for now. Okay, so because Z implies this, right? If A implies B, then probability of A is less than or equal to probability of B. So that's the fact that we are using over here. One more step. This is a somewhat technical step which we need to do. So don't, I think, worry too much if you don't get this, the reason we are doing this. Okay. Now, what really did we do? So if you see this, right, what we have written down here has inside of this probability things like UTA, right? So UTA is the random variable at time t, right? We really don't know how many times arm A got pulled. Of course, because there's an and here, we know it got pulled more than U bar TA times, but that can be any number, right? Starting from U bar TA all through to infinity. Now, in order to apply Hoeffding's inequality, right? I mean, remember when we did Hoeffding's inequality, we were told you've been given U samples, and then you try and bound the deviation. That number U needs to be a fixed number. It cannot be a random variable as it is over here. Okay, so it's got to be 1 or 2 or 3 or some number that is sort of given as a constant beforehand. So really there is a need for us to translate this statement, this sum of probabilities, into something inside of the event that has fixed numbers rather than random variables. And the way we do it, right, which is maybe the simplest way of doing it, is to do the following. So let us denote by P hat AX, okay, the empirical mean of arm A after X pulls. Okay, X is a number that here you can see it goes from U bar AT through T, right? Similarly, Y is for the optimal arm. Y is a number that goes from 1 through T. y is the empirical mean of the arm after the first sort of p hat star y is the empirical mean of the optimal arm after y pulls of arm star. Okay. Now, in reality, right, when you're running the algorithm at time t, maybe arm A has been pulled 23 times, maybe arm star has been pulled 40 times, right? But we don't know this 23 and 40. Another time you run it, right? Maybe at the same time t, arm A has been pulled 57 times and arm star has been pulled 3 times. We don't know what these are. So we are accounting for all possible configurations of numbers of pulls to have happened, right? So if this has happened, then certainly one of these things must have happened. What are these things? These are rewritings of p hat t a in terms of p hat a x, okay, and p hat t star in terms of p hat star y, where x and y are varied from in the corresponding ranges. Okay, so what you need to be convinced of is if this event has happened, then one of these events must have happened for some x and y. Okay, I mean, in fact, we won't encounter all these x's and y's, but certainly we would have encountered at least one pair x and y that make this happen if the event on the second line has happened. Okay. Now, one thing also to note is the algorithm might actually very well stop before, for example, arm A has been pulled a certain number of times, right? Or arm star has been pulled a certain number of times. So, I mean, it might appear to you that these might not even be well defined, right? Maybe the algorithm never pulled arm A x number of times the way we are varying x. But it is still possible to think of these as well defined quantities, because think of an alternative sort of way of running UCB, right? So what you do is you take each arm, you just sample it lots and lots of times, maybe an infinite number of times, okay, and keep it, okay, and it is these empirical means from those infinite runs that are being calculated as p hat ax and p hat ay. When you're actually running the algorithm, at that time just go copy over whatever you had sampled and recorded, okay. So the algorithm might well stop without visiting all the infinite pulls of any particular arm, right? So let's say we generated the pulls beforehand, and so these quantities are well defined, but the algorithm might stop before encountering all of them. Okay, so clearly this is a slightly heavy slide, right? The concept here is a little bit subtle, but the point is, in order to apply Helping's inequality, we need a constant x and a constant y, right? So this is literally saying take x to be u bar at plus 1, u bar at plus 2. We are fixing it before looking at what is going on inside. Similarly for y. Okay. So what we have done is to say that b is this quantity which is upper bounded by now a slightly larger probability that, I mean, to say this in English, maybe you will say something like the UCB of arm A after x pulls compared with the UCB of arm star after y pulls. Okay, all right. So this is the quantity that we will look at in the next slide. So let's consider any fixed x and y from that. So what was happening inside that probability was this event, right? The probability that the UCB of arm A was exceeding the UCB of arm star. Now, I'm going to make a funny looking claim. And that claim is, if the UCB of arm A is greater than or equal to the UCB of arm star, then the UCB of arm is greater than or equal to P star, okay, or the UCB of arm star must be less than P star, okay. So, I mean, this P star is clearly a rabbit I have pulled out of a hat, but this statement, right, follows from a simple mathematical fact. You take any alpha, beta, gamma, right, literally any three real numbers, the greater than beta, right? Maybe this should be alpha greater than or equal to beta. Then there's a small typo here. This should be alpha greater than or equal to beta, right? Consistent with what we have said. Then either alpha is greater than or equal to gamma, or beta is less than gamma. Okay. So yeah, I mean, fill this out with examples, and you'll see that this is true. So all we have done here is taken gamma that's going to help us. Okay, and that choice of gamma is P star. So we've taken alpha to be the UCB of arm A. We've taken beta to be the UCB of arm star. We've taken gamma to be this quantity P star. Magically, it looks for now, but it's going to be useful for us in order to come up with our bound. All right. Okay.